Check it out now, y'all.
NanoHub U, online instruction.
Hello, and welcome to Thermal Resistance in Electronic Devices, an online short course, Part 1. My name is Eric Popp from the Department of Electrical Engineering at Stanford University, and in the first of a series of 4 short lectures, I would like to introduce you to some of the basics as well as a few advanced concepts of thermal resistance in electronic devices. So what are the goals and audience of this short online course? I'd like to, first of all, discuss heating in nanoscale semiconductor devices. I'd like to achieve a fundamental understanding of how heating occurs. And I'd also like to touch upon the role of heating in electronic circuits, of course, in terms of reliability, the role on flexible substrates, which, for example, have poor thermal conductivity. And also, we will briefly touch upon the role of heating in devices such as SOI, modern devices like FinFETs, the role in phase change memory, carbon nanotubes, I should add, a little bit in nanowires, and so on. And also, I think a very important goal of this course is to understand how to do practical calculations in fairly simple terms, such that we are able to apply them, for example, in our labs while we are conducting actual real-time measurements. The intended audience of this course is upper-level undergraduates, graduate students, and industry researchers, basically folks who are involved in research in this area. The only prerequisite is basic semiconductor devices, as you will see, perhaps a little bit of quantum mechanics, basic transport physics and semiconductors. But I think a course on basic semiconductor devices should cover most of the concepts that we will need to proceed over the next 4 short lectures. The topics that I'd like to cover by lecture are number 1, basics of Joule heating, number 2, heating in devices and circuits, number 3, thermal resistance and estimates, and then number 4, device thermometry. So let's get started with the first lecture, the basics of Joule heating. First of all, why are we interested in this topic? Certainly we understand that power dissipation is a major concern in semiconductor electronics. Higher packing density, of course, of devices and transistors has led to higher power density, as high as, if not greater than, about 100 watts per square centimeter. Confined geometries, for example, in FinFETs or nanowire FETs, are, of course, a challenge. Some of these materials that are involved actually have poor thermal properties. Of course, SiO2 is a classic example of a material very much involved in the fabrication of devices and circuits with very poor properties, very poor thermal properties, I should add. And of course, there's the issue of material boundaries. As you can imagine, as I'm sure as you know, as devices get smaller, the surface area to volume ratio of these devices actually becomes more important. And I'm just going to highlight a few interfaces present in a device in this picture right here. This is a cross-section of a device. And of course, there are interfaces all around where I'm highlighting between the gate, the source, the drain, the contacts, of course, and so on, everywhere where there are 2 dissimilar materials. I'd like to discuss where the heat is generated in these devices. And what do I mean by that is I'd like to understand spatially where the heat is generated, for example, in the channel or the contacts in a transistor, as well as spectrally in terms of the function of energy. How is it generated in terms of the acoustic or the optical phonon modes, and so on, whether it's in longitudinal acoustic modes or longitudinal optical modes. Let's also briefly discuss the thermal effects on devices. So first of all, I think this is fairly clear to anyone who's worked with semiconductor devices. Temperature typically rises during operation. And one of the things that occurs is as the temperature rises, the threshold voltage typically actually comes down because thermionic emission over the barrier at the source side of the channel becomes easier. So, of course, one of the results of the threshold voltage coming down is that the current actually goes up. At the same time, mobility is also known to decrease as the temperature rises due to increased phonon scattering, electron phonon scattering, which, of course, actually leads to the opposite effect, which is that the current should decrease as the temperature increases. And there are very simple expressions essentially shown for threshold voltage and for mobility over here. As you can imagine, typically eta will be negative, and typically alpha here will be also negative, in order to illustrate the examples shown over here. So a priori, it is perhaps difficult to say exactly what will happen to the current as a function of temperature in a device, but I think it is generally accepted, generally fairly well known, that at least in the saturation regime, the mobility decrease, the increase in scattering, will actually dominate, and the threshold voltage effects will typically dominate the subthreshold regime, sub-VT regime, as we will see a little bit later. Okay, the other aspects that I'd like to discuss, which I think occurs to all of us, or we've experienced by all of us who have ever done device characterization, is that during characterization, the device will heat up, especially if we do DC IV curves. Similarly, we know that temperature varies during digital and analog operation. And so therefore, the very, very simple DC, or the simplest DC IV curves, are actually not the true IV curves of a device during operation. So how do we learn to account for those? By the way, this is true whenever the thermal time constant is actually significantly longer than the electrical time constant, and of course as long as the input power is high enough. So we will see also what this means. This is largely true for all the nanoscale type of field effect transistors listed down here, SOI, certainly FinFETs, carbon nanotube FETs, transition metal dichalcogenide FETs with fairly low thermal conductivities. Nanowire FETs, of course, have significant boundaries. So all of these, as they are measured, the power dissipation actually significant and the thermal resistance significant as well, leading to significant temperature rise. So again, this is a goal of the course, is to try to understand these device thermal parameters at the same time or on the same footing as the electrical ones, and of course the electrical ones being covered in most semiconductor courses. So what are the simplest power dissipation models, the ones that we learned essentially in high school or even at the earliest undergraduate level? The simplest device, of course, is something like a resistor, and the simplest power dissipation model in a resistor is something like IV or V squared R or I squared R. This is by far the simplest model that we can come up with. Perhaps if we talk about power dissipated purely within the device, we should subtract the contact resistance. So in that case, it becomes I squared times R minus RC. But this is probably the only correction we can make at this point in this very, very simple lumped model. The drawback with this model is that we have no idea, we don't know where the power is dissipated, whether it's dissipated in the contacts or in the middle of the channel or near the drain or the source end of the channel of a transistor. We also have no idea whether high energy or low energy phonons are generated. We just know roughly the total amount of power in watts which is being dissipated inside the device. Let's also briefly review the operation of a digital inverter. A digital inverter, as is drawn over here, consists of an N-type device and a P-type device. And by device here, of course, I mean a field effect transistor. As the input voltage goes high, the output voltage will, of course, go low. Because when the input voltage goes high, the N-type transistor will turn on and the P-type transistor will turn off. Therefore, the current will flow as the arrow shows over here, thereby bringing this node down to ground. Okay? All right. What I claim over here is that the power dissipated inside a digital inverter is FCV squared during operation. This is the active power, where F is the frequency, C is the load capacitance over here, and V is the operating voltage. Why this occurs, I think, should become clear pretty quickly. First of all, let's consider the energy dissipated, or the energy actually stored and of course dissipated during operation. As the N-type device discharges, the capacitor, the load capacitor, will discharge, which is an energy of 1/2 CV squared. On the next clock cycle, the P-type device will be the one actually turning on, and the N-type device will be the one turning off. And so, therefore, the capacitance will now charge up. Again, the energy required to do that is 1/2 CV squared. So in one case, this is on the up clock cycle, and on the other case, this is on the down clock cycle. This is the full period, of course. The period is essentially shown over here. This is the full period, which is also 1 over the frequency, right? And therefore, the power, of course, is energy divided by time, and that will be frequency times CV squared, because we have a capacitor charging on the up cycle and discharging on the down cycle, essentially. This is actually quite important as well, and also a very, very basic and obviously easy to derive power dissipation formula, because it reminds us that in digital circuits, frequency, parasitic capacitance, and voltage are by far the most important components. This, by the way, also explains why the frequency in recent digital circuits has plateaued at about 2 to 3 gigahertz for many, many years now. And also explains why many designers are most interested in lowering the voltage. So, of course, if you lower the voltage by a factor of 2, you actually gain in power by about a factor of 4, because the digital power goes as voltage squared. And, of course, it's also very, very important to lower the parasitic capacitance. Let's look at a very simple model for a very simple one-dimensional resistor. This is what I call a Landauer resistor. What is shown over here is the electrical resistance for essentially two electronic modes, or two electron modes, traveling between a source and a drain with chemical potential or Fermi levels mu1 and mu2. These are not mobilities, these are actually the chemical potentials. Of course, the difference in chemical potentials is the voltage applied, so I think everything should be fairly clear over here. The reason this shows up as h over 2q squared is because the factor of 2 comes from the 2 electron spins. H, of course, is the Planck constant. Q is the elementary charge. L is the length of the conductor, in this case, of the little resistor. And lambda is the mean free path of electron travel within the resistor. So the question that I want to answer here very, very briefly is, where is the power dissipated and how much of the power is dissipated within this little resistor? Let's assume that the resistor is actually ballistic in the first case, right here on the left. If the resistor is ballistic, that basically means that an electron injected from the source will travel all the way to the drain without any kind of a scattering event, as the arrow shows over here. Therefore, all the power will be dissipated actually when the electrons reaches the drain and it starts scattering with the phonons inside the drain. There's actually no power dissipated inside the channel, so the P equal to 0, and the power dissipated inside the drain is actually equal to the total power, IV, that is essentially calculated above. The exact situation is actually slightly more complicated, and of course it depends on the Schottky, if there's a presence of Schottky barriers. In this case, of course, the contacts are assumed to be perfectly ohmic, in fact, perfectly conductive contacts. But this is basically the gist of the story. On the other hand, if I have a fully diffusive resistor, what I expect is for the electron to be injected into the channel and then to scatter very quickly. Then it'll travel a little bit more, it'll pick up energy from the electric field, and it'll scatter again. It'll pick up energy, it'll scatter. It'll pick up energy, and finally it'll reach the drain, but with much diminished energy. In this case, most of the power, as you can see, is actually dissipated inside the little channel, and of course there's very little power dissipated inside the contacts. I should also label the mean free path over here because it's not too difficult. The mean free path in this case, of course, corresponds to the distance between two scattering events over here. Okay. So maybe this is a slightly better drawn image of the previous discussion. There's essentially these three regimes: the diffusive regime, which we already discussed, where this distance right here is the mean free path. In this case, of course, the length of the conductor is significantly longer than the inelastic scattering mean free path. This is essentially the classical case. This is corresponding to any kind of resistor, large bulk resistor that we've ever measured in the lab or we have at home and so on. And of course, this is where continuum approximations, Fourier's law for thermal and so on applies. The in-between situation between the diffusive and the fully ballistic case that I described earlier is actually this quasi-ballistic regime described over here. So in the quasi-ballistic regime, the length of the device is actually comparable to the mean free path. Right? It's on the same order of magnitude as the mean free path. Not significantly shorter, not significantly longer. What is shown over here is essentially the mean free path for optical phonon scattering. This is the energy required to emit an optical phonon in this particular case. And for the way this device is drawn, there's only 2 or 3 scattering events inside the channel. And so there's only a couple of phonons which are being emitted. And some of the hot carriers actually can still escape to the contact and therefore heating up the contact. This is not necessarily an easy regime to treat with the continuum approximation. And so therefore, usually this regime requires Boltzmann transport equation, Monte Carlo type approaches, although there are some simple approximations we could also make here. Another more peculiar regime I'd like to show is here in the bottom image. This is near a barrier. So what happens near a barrier is, or to understand what happens near a barrier, we actually have to remember that the electrons which are traveling from left to right are actually distributed according to some sort of a distribution, which corresponds to the temperature and the Fermi level on the left side, to the left side of this barrier. What happens when these electrons reach the barrier is that the electrons with energy less than the barrier height will simply turn around, will be reflected. This is, of course, assuming that the barrier is not significantly thin, in which case tunneling would also contribute. So in this case, I'm actually considering purely thermionic emission over the barrier. All right. On the other hand, electrons that have energies over the barrier will essentially be able to thermionically emit over the barrier. So you can imagine what's going to happen is the barrier is going to act as an energy filter, such that only the electron energies with energy greater than, only the electrons with energy greater than the barrier height will be able to transmit across this barrier. And therefore, the distribution that is left to the left of the barrier will be significantly colder, right? So what is essentially happening in this case is that we will have heating to the right of the barrier, and we will end up with net cooling to the left of the barrier. Heating to the right of the barrier because, of course, the electrons that have made it over the barrier will eventually have to relax their energy to the lattice. So we have a very, very interesting asymmetric transport property across this barrier, again, with cooling to the left and then heating to the right of the barrier. We will come back to the tunneling effects because these actually require quantum treatment. But this is a very, very simple example of thermionic effect. Okay. Now I want to spend 2 quick slides looking at a continuum view of heat generation. So again, we've discussed power, the lumped model, the simplest model. Power is I squared R. I think we understand that. It's fairly simple and straightforward. Now, if we want to solve, for instance, a finite element model of our device, this is some tool like a Centaurus or Medici or Field Day. So any of these finite element models typically will model the heat generation per unit volume, watts per, let's say, centimeter cubed, as the dot product of the current density and the electric field at any point along the mesh or across the mesh. The current density, of course, is amps per square centimeter. The electric field is volts per centimeter. And of course, you can see how you end up with a power density in units of watts per cubic centimeter in the simple representation. This is not a bad approximation. In fact, it gives us the spatial distribution of power dissipation, which is something that the lumped model described just above is unable to do. There's essentially no spatial information here, no spatial info. Okay. Perhaps a more complete finite element model would actually include not just the dot product of the current density and the electric field vector computed across the device mesh, but also the radiative, or rather the net radiative rate. This is essentially R minus G, the recombination. I'm sorry, I shouldn't have said the radiative rate, but rather the recombination, the net recombination rate, the recombination minus generation. What I did mean to say is that one should be careful about radiative recombination versus phonon-assisted recombination. Here, of course, I'm referring to phonon-assisted recombination, which results in either net cooling or heating of the lattice. What might be a little bit surprising to you here is to see the second term here multiplied not by the band gap, but by the band gap plus 3 kT. Where this comes from is the fact that the average electron above the band gap and the average hole below the band gap, on average, of course, have an energy of about 3/2 kT. This is just a very, very simple approximation. As you can imagine, if you have 3/2 kT on the electronic side and then 3/2 kT on the hole side, then the total energy that is actually being relaxed across the band gap is not just the band gap, but the band gap plus 3 kT. So that's where essentially this second term comes from. All right. Now, if we were to look at direct band gap materials, of course, we would also need to subtract the optical recombination power. And here again, we have the same current density, J. We have the band gap, which could be corrected for 3 kT. And we have the optical quantum efficiency, eta optical. Q, of course, is the elementary charge. If we want to become even a little bit more sophisticated, we can also include thermoelectric effects, either inside a material, a continuum type of thermoelectric effect. This is also known as the Thomson effect, or the thermoelectric effect at a junction between two materials, for instance, Peltier cooling or thermoelectric Seebeck, essentially heating. And so this is not too difficult to include inside a finite element model. This is essentially just the absolute temperature multiplied by the current density and then multiplied essentially by the difference or the gradient in the Seebeck coefficient at any point or across any 2 points across the semiconductor. At the bottom here, I said if we are actually simply to look at a junction between two materials, A and B, then we replace the current density with raw current, and so therefore the power generated or absorbed at this junction is the temperature multiplied by the current, and of course multiplied by the difference in Seebeck coefficient across the two dissimilar materials. So this is essentially how we can incorporate pretty much all the relevant heat generation or heat or cooling, heat absorption mechanisms in most semiconductors. Before concluding, I just wanted to essentially write down in one place what is probably the most complete heat generation model that you could include in a finite element type simulator. This was written out by Lindefeld in 1994. He literally calls this the final formula for heat generation. I have these references on the next page right as we wrap up the short lecture. Of course, we recognize the most important terms in the heat generation regime are the dot product of electric field and current density, then of course the net recombination, non-radiative recombination multiplied by the band gap plus 3/2 kT. Then we have gradient terms in terms of the electron affinity. And then of course we have all the Peltier and Seebeck terms over here. And way at the end, we even show, or he even shows rather, terms which depend on the temperature dependence of the band gap, which we had actually not discussed so far. But it's basically the first few terms which are the most commonly occurred or encountered in semiconductors, as we've discussed so far. I will wrap up this first short lecture by proposing a few review articles for further reading. Gerhard Vahutka's Rigorous Thermodynamic Treatment of Heat Generation in Semiconductor Devices. Lindefeld's article, which I had just mentioned a slide earlier, with the most complete formula for finite element type heat generation that I'm personally aware of. Then a review article which will also crop up in later parts of this short course, which I wrote about 5-6 years ago, and a more recent review article which will also come back to later, which contains additional discussion of various heating mechanisms in semiconductors, going a little bit beyond the scope of this short course.